A reminder that we're going to have a quiz, a short quiz, right, over work and power on Monday. I don't expect that it'll be super long. Just, again, to clarify, you need to know how to calculate work. You need to know how to calculate power. You will not need to do any crazy conversions. You will not need to know how to do sine, cosine, tangent stuff. That said, the idea of what we learned in the ramp lab is fair game. Does that make sense? So the mathematics of it might not be there, but the concept behind it is still there. So I just want to make that really clear. And then there are 2 quick questions for homework for Monday that will stem from the stuff that we're doing today. Sounds good? All right, here we go. Unfreeze my screen so you can see the topic for the day. Well, it's hard to read. Work. We're talking about work. Is that great? Yeah. Do you feel like we've talked about it before? Yeah. My friends are right over here. Can I have your attention instead of listening to chatter on the back end of that? We've defined work already, haven't we? How did we define it before?
Distance times
force times distance, or distance times force. And there was something that had to be true about that distance and that force. Yep, they had to be in the same direction or in opposite directions, right? Yep, but they had to be pointing in the same plane, I guess is a nice way to say it. I don't know if you remember way back to the day that we defined work. You all wrote this down, or you told me these things to write down. There was a word that kept popping up in all of your definitions. What was that word that kept popping up that I said, another day? Energy, right? Today is the other day. Today is the next day that we're going to talk about that. So here it comes. So work can be defined as force times distance. That is absolutely fine. That's true. It's not inaccurate. But work can also be defined as, are you ready for this? This equation is going to blow your mind. Not really. It's wild and crazy. Work is equal to the change in, that's delta, right? Delta just means change in energy. That's it. Put your pencil down, right? Like that's it. That is the equation. Perhaps the easiest equation that we're going to write down all year, right? One thing equals another thing. Okay. Got one, got the other, we're done. All right. So that's all well and good once you know what this thing is, right? Well, it is force times distance. And so you can see the force times distance is equal to change in energy. Like that's a true thing. But this thing right here, oh, by the way, I have to tell you that it has a name. It has a name, and we like to name things. So we'll talk about this as the work energy theorem. The work energy theorem. It's pretty darn straightforward. Not a lot of stuff that kind of blows your mind in this, but it is important. But again, we have to define this energy business in order to figure out what it is. So we're going to do another brain dump. Are you ready? Here it comes. I don't want you to tell me the definition of energy this time, though. I want you to just tell me some examples or types of energy that you know of. Okay. So I'm going to give you just a minute. This is you and your brain. I'll let you share in a minute, but right now, just you and your brain, write down as many types of energy as you can think of. Go. In your head, man. Your head, your people, your paper, your pencil. It's okay. It's all right. We'll get there. Sometimes instructions are hard. Write them down. Write them down. Make a list. Write them all down. All right, are you done? Is your graphite finished? Okay. If you're sitting at a table by yourself, find a table with more people than just you. Consolidate your lists. Make them longer. Go, go, go. Talk to your table mates. You write down everything that they have unless you have it written down already. Make the lists longer. Go, go, go.
Potential or lack of potential.
I didn't do it. I went.
How do you do that? Nope.
It's very flavor.
Is there such thing as friction?
All right. I don't know why my, there we go. All right, Josie, give me one.
Like kinetic energy.
Kinetic energy. So the way that this game works is that if somebody says one that you don't have written down, you add it to your list. So at the end of this little activity, we're all going to have all of them written down. Are you with me? All right, Matt, your turn.
Combustion.
All right, Stella.
Potential.
All right, Maya, what you got?
Solar.
Okay. Ryan?
How about cosmic?
Can you tell me what you mean by that? And the answer can be, I don't know. Okay, just sounded good. Awesome. All right, Jordan, what you got?
Hydro energy. Yes, I knew. From like the ocean. I don't know.
Okay. Emma?
Heat energy.
What's that?
Heat energy.
Okay. All right. Let's see. We'll put them together in just a minute. Hold on just a sec. What?
I was going to say, would heat energy go under thermal energy?
We can, do you want to add thermal? I would say heat and thermal are pretty much the same. You got one, though, go.
Static energy.
Like, do you mean electricity?
Yeah.
Okay. Okay. All right. Who have I not talked to? Monse, what you got? Nuclear? Mm-hmm. I've lost track. Isaac, go.
Elastic potential. And then there's another one too. That one too. Gravitational potential. I use resources.
You used, full disclosure, he just told me he did use resources. He's not just pulling that out of his whatever. All right. More. Wave energy? For sure. Yeah. Yeah.
Gamma energy.
Okay. We'll talk about that in a second, but yeah. What else?
ATP.
Your bio teacher will be proud of you. What else? Light? More.
Sound.
Kind of.
Kind of.
Sure. In this exercise, yes.
Okay.
I'll give you that. Yeah. More. Put your lab away, ladies. Put your lab away and do this with me. What else you got? Atomic? Maybe? You've hit most of the big ones. There's one that we talk about a lot here in Iowa. What's that? Wind energy. Uh-huh. What did you say?
I was just about to say wind energy.
Oh, sorry. Yeah.
It's subatomic.
Not real. Like nuclear energy is subatomic technically, but there's not really. I mean, you can say like mass energy. We can say there's energy associated with mass. Any mass has some internal energy. Yep.
What type of energy goes into a battery?
Chemical.
Volcanic.
What?
Volcanic.
Volcanic energy?
I don't know. There might be
Can you? I don't know what you're describing.
natural energy. Volcano erupts. Has like energy.
Yeah, but I don't think that it's a unique kind of energy in the way that we're talking about these things. I'm gonna not write that one down. Is that gonna break your your heart? Or is it okay? Okay, yeah.
Physical energy.
What do you mean?
It's like I don't know, we're in physics class. I was just thinking outside the box. So
I like it when you make when you actually admit that. At least that's good. That's good. Any others you have on your list? This is a pretty good list, you guys. I'll give you credit for it. It's a good list. All right. So some of them you weren't so sure about. And some of them kind of go together in ways that you may or may not realize. So I wanted to share that with you. One case of that is light energy and where did gamma? So gamma rays are a type of light, right? Gamma rays are part of the electromagnetic spectrum, and light is all of the electromagnetic spectrum. So this, I would call this all electromagnetic radiation or electromagnetic energy, okay? And in fact, it's kind of weird, but a lot of that electromagnetic radiation and electromagnetic energy is really just thermal energy. It's a kind of thermal, okay? Yeah, so that's one that they're kind of similar, kind of can put together. Similarly with waves and sound, sound is just a kind of a wave. We'll get into that and talk about that a little bit more and kind of pull all those pieces together soon. Go, Ben.
Yeah, go to the bathroom.
You may. So there are two kind of big, big types of energy, kind of two overarching categories, I guess. The first one is kinetic. So hopefully you've heard that term before. And the second one, the opposite of kinetic, is potential, okay? So I want you to put boxes around those or circles around those or write those in a separate place because we need to define those in particular. So in some cases, like in our physics class this year, we're going to talk about kinetic energy just as kinetic energy. What does kinetic mean? What does the word kinetic mean? Do you know? It does. It does. It means the energy of movement. So anytime anything is moving, it's got kinetic energy. Okay? I said that kinetic and potential are kind of opposites. What is potential energy? What does that mean to have potential energy? Do you know?
There's something that's still but could move.
Yeah, it could do something, right?
Yeah.
I don't know. I'm sure that you have not heard this from your parents, but probably, perhaps someone that you know has heard this from their parents. You know, you're sitting on, not you, somebody else is sitting on the couch playing video games, and their parent says something like, you know, you have a lot of potential, right? If only you get up and do something with it. Have you ever heard that? Maybe, hopefully not from your parents telling you that, but to have potential means that you could do stuff if you wanted, right? If only you started, like you said, started moving, started doing things. Potential energy is what we call like stored energy, okay? So it's energy that's stored up It could do work. It could make something happen, but not just that way. When it's stored up, it doesn't really do anything. It just has it there. So what I'd like you to do now, those are the two big ones, kinetic and potential. My argument to you is that every other kind of energy in this list can be classified as either kinetic or potential. So I'm going to give you a minute with your table mates to have that conversation and write a K or a P next to each of those types of energy you've got on your list. Okay? Do it.
Okay, combustion. Yeah.
No? You're not talking about birds and government shutdowns, are you?
I should have. It's
All right.
government shutdown.
All right, Leanne, we're going to start with you. Pick one. What are you talking about?
Light is kinetic.
Light is kinetic. I agree. That means gamma is kinetic too, right? Why is it kinetic? Because it moves. It's a wave and it moves through space, right? So which one do you want to do, Isaac?
Sound.
Oh, okay. Those should not be surprises to you, right? Sound waves travel through from my vocal cords to your eardrums, right? It has to be moving. It has to be moving. It is motion energy. It's kinetic. All right. Let's see. Stella, what you got? We're just going to go one for everybody.
Wind.
Wind is kinetic, right? Wind, like the definition of wind is that it's moving air. Moving air. Moving kinetic. All right. Awesome. All right, Jordan, go.
Solar is kinetic
Solar is kinetic. Do you agree?
because it's light.
Okay. Solar, I would argue, is both. Or one can make an argument for both. So I would agree that it is kinetic if you talk about the actual light that is coming from the sun. But you can also make an argument for the stored energy, like when you actually collect that energy from the sun. Does that make sense?
Yeah.
So you can make an argument either way. They look like they want to fight with you. So I'm going to talk to Emma next. Go, Emma. She's like, wait, what?
Hydroelectric, would that be kinetic because it's moving?
Absolutely. Yeah. For sure. Sorry, I'm not trying to pick on you guys. I'm just trying to find out. They're really upset. So I'm going to ask. Josie, go ahead.
We don't want to fight with you. We have
No, we
suggestions.
want
I-
to have a suggestion.
Oh, okay. Go. There are a couple that are really, really easy because they have the word in them.
Well, yeah, but I don't want to do.
You don't want to do one of
It's
those?
fine. I could, yeah, like elaborate.
For sure, it is. Yeah. I just wanted to let you off the hook. What, Ben?
Chemical is potential.
Chemical is potential. Okay. If you have a battery, do you guys learn in chemistry how a battery works? Yes?
That's
Yeah.
what I was thinking.
Yeah. Like it's a chemical reaction. It has potential to do stuff, to make electrons move, but without something to do that, all you got is the potential. Right? Just like you sitting on the couch playing video games. All right. Coming back over here, Mom, say what you got.
Atomic would be potential.
It is potential. Awesome. Good answer. Atomic is potential because atoms are all happy and, doing their thing. Electrons doing their thing and nucleus doing its thing. When you break it apart, though, right? Atomic bomb, we've heard of that, yes? When you break apart an atom, energy is released. Energy is released. Gamma rays, light, right? Then kinetic comes out, but until then, you've got potential or stored energy. Nice work. All right, Matt, what you got?
Cosmic is kinetic.
Cosmic is kinetic. Now, I'm going to say that I'm not exactly sure, but if we're thinking of cosmic energy as in terms of like the electromagnetic radiation coming from other stars, is that maybe what we're thinking of? I don't know for sure what the...
Well, I was just kind of thinking of the movie of everything.
Wait, what?
Never mind. Okay.
No, tell me, because I want to know what you're talking about.
Like the movement of everything.
Oh, the movement of everything.
Yeah.
Ah, okay. I will buy that. Interesting. Okay. That's fantastic. All right. Ryan, you're next.
Combustion is
Okay.
kinetic.
Okay. Because why?
Well, it's combusting.
It's combusting. So that one, I kind of feel like with solar, I think you could make an argument like the actual, the process of combustion, right? I would argue absolutely is kinetic. If you think about something that is combustible, right? Those, things that are marked combustible, that has a whole lot of potential energy that if given the kick in the right direction, then we'll go boom. Yeah. So I think if you're talking about the actual process of combustion, then absolutely I would agree that it is kinetic. Yeah. All right, Stella, what you got? Oh, rats. What else do we have left? A few.
Is he thermal kinetic?
It is kinetic, absolutely. Everything that exists has a temperature, right? Or a temperature above absolute zero. And the reason for that is because the molecules are moving, the atoms are moving, the subatomic particles are moving. Moving gives you heat and therefore thermal energy. Absolutely. All right, we got a few left. Who wants them? Go, Jordan.
Is ATP a potential?
I would think so. I don't know. I'm not a biologist, but that's my guess. What does ATP stand for? I don't remember.
I don't know.
Too many bio people in here?
Did anybody work on this before?
I think it was too long to like remember. I was like, what?
I'll ask Oz today at lunch. Yeah.
Gravitational potential is potential.
Hey! Gotta take it, right? Whoop, that got little. All right. So we've got mass energy, we've got biomass, we've got nuclear. I'm just looking to see what else we haven't marked yet. Geothermal and static. Those are the ones we got left to talk about. Go.
Mass potential.
Is potential. Absolutely. I'm hoping, depending on how our like pace goes and time goes, I'm hoping that we get to talk a little bit about mass energy. You've seen this equation before, yeah? Yeah. This is the energy mass equivalency, right? So anything with mass has energy innately in it, and that's where it comes, like that's how it all works together, and it's potential energy. Yep. All right. A few more. What do we got? Biomass? What is biomass? Do you know? Sounds fancy.
It's like organic stuff.
Organic stuff. What do we do with that organic stuff to get energy? It's potential. It's sitting there, right? It's got a lot of ability to do stuff. Yeah. That's potential. Nuclear? Potential. A lot of potential, right? Yeah, nuclear bomb, boom. But there's got to be something that pushes it. Absolutely. Nuclear goes boom. But it has potential until then. All right, static electric energy, static electricity. Think about this one carefully. Do you know what static electricity is? Maybe not.
Lightning.
So, yes, so lightning is the release of static electric energy. Maybe I'll say that.
Could be both.
Why do you say?
Well, I mean, so you could just like have it if you're just like walking around. Like, I mean, if you're just sitting there, you have sweatshirts on and then a shirt, then you can also get like rub your socks on the carpet.
Mm-hmm. Did you want to say something? Yeah. So the actual static electricity comes from rubbing your socks on the carpet, right? You collect a bunch of electrons, and then you are charged. So you have a high amount of static electricity. And then as soon as you go over and reach out and try and, zap somebody or something, then it's moving. That's the lightning bolt, okay? But until then, static electricity is potential energy. Cool. All right. Well, I hope that this was like not a waste of your time. I hope that this kind of like broadened your head into what energy could be. We also know that as energy changes, the amount of energy changes, work is done. In this class, we're going to talk about 3 particular kinds of energy, okay, and we're going to define them. Most of these kinds of energy are physics related, sound and wave and wind and atomic and mass energy. Some of them we leave to the other scientists like chemical energy, biomass, ATP, some other things, just so that they have something to do too, because that would be mean if we took everything for physics. But most of this is stuff that we would do in physics. Most of it is not what we're going to do this unit, though. The 3 things that we're going to focus on this unit are kinetic, and we're going to talk about it just at a macroscopic level. So we're going to talk about objects moving, okay? We're going to talk about gravitational potential. We'll define what that means. And we're also going to talk about spring potential or elastic potential. And believe it or not, we're going to go back to the lab that we did at the end of 2018, that last day right before break. Remember we did that, the springs? We'll bring that back to this later, not right now, not today, okay? So those are the three kinds of energy that we're going to deal with, that we're going to talk about. And we're going to jump in because we've got a little time, and why not, right? So let's do this. Do you have a preference? What do you want to start with? I don't really care. Gravitational potential? All right, let's do it. Thanks for making a decision for me. I appreciate that. All right. All right. So let's write down what we know about gravitational potential energy. It's going to be energy that's stored, right? And not only energy that's stored, the other part of the definition of potential that I probably should have written down is energy based on position. Okay? And in this case, we're talking about the energy that's based on position in what they call a gravitational field. And in this class, that gravitational field is going to be that of Earth. Okay? We've had the frog out a few times. Where did he go? Is he hiding? I don't know where he is. I'll use a cheeseburger today. That'll work. I'm sure he's around. I just can't find him off the top of my head. If I let the cheeseburger go, what's going to happen to it, guys? It's going to fall, right? And it's going to squeak when it hits the ground, right? Now let's think about the energy that it has based on position. If I hold the cheeseburger here, I just want you to think about this without having a definition or anything like that. If I have the cheeseburger here, and then I move it here, which one do you think has more of this funny energy that I'm calling gravitational potential energy?
Right there.
This one?
Mm-hmm.
Why?
Because it accelerates when it goes down. So it has more time to accelerate.
Has
It's
more
faster.
time to accelerate, more time to do stuff, right? Does that make sense? That gut feeling is exactly right. That's exactly what it is. Gravitational potential energy, I'm going to write it down the way that they do in your book because I don't remember which. Okay, they use PE sub G. Different books use different things. Hello. They define potential energy gravitational, okay, as the mass of an object times the acceleration due to gravity, which we know is 9.8 on the or near the surface of the Earth, times, just like Ben was saying, the height. Okay? So if you want to quantify or tell me how much energy the cheeseburger has based on its location, based on its position, this is the equation you're going to use. Mass, acceleration due to gravity, so this is on Earth, 9.8 meters per second squared. This is the height. Okay. Now, before we get too far into this, too far into the weeds, I do want to make sure that we look at the units here. Does that sound okay? What are the units of mass? Always have been, haven't they?
kg,
What are the units of acceleration?
meters per second squared,
Uh-huh. What are the units of height?
meters.
Okay. So gravitational potential energy is measured in kilogram meter per second squared times meters. Sounds like a horrible unit to have to write down every time. Can we simplify that at all? Can we?
Kilograms meters per second.
What is this?
Newton, yeah, meter.
This thing in the box is a Newton, right? Mass times acceleration. It's a Newton. So I can say that potential energy gravitational is a Newton meter. Also kind of an annoying thing to say. Any better choice? What's a Newton times a meter? Do you remember?
Force times distance.
Joules, right?
Is a joule.
It's a joule. Yep. Gravitational potential energy is measured in joules. It's good. It's a really good thing that it is because I'm going to remind you.
Change in energy.
Right.
So
And
it's
so
in
if this wasn't in joules, we'd have an issue, right?
Yeah.
It's got to be joules and joules. Okay. All right. I'm going to give you a problem. Oh no! Now we're running out of time. Oh dear. Here, let's get started on this one. Okay, I want you to do this problem real quick for me. How much gravitational potential energy does a 0.6 kilogram frog have when he's held, or she's held, I guess, 0.65 meters above the table? So imagine that my cheeseburger is my frog. 0.65 meters, boop, like this. What's up?
Can I use my phone calculator?
I'll get your calculator so fast.
Thank you.
You're welcome. Can you do this one?
It's good.
Yeah.
Are there, like points on the Earth where gravity isn't like
Uh-huh.
the same.
Uh-huh. Yeah, it's just an average at sea level. Here, it's not exactly the same. If you Google, like, acceleration due to gravity on Earth, you can, like, actually get maps. And geologists actually use that to figure out what the core and the mantle of the Earth look like. Yeah, based on the density of that stuff and how the force is pulling. Yeah, it's kind of weird.
It's insane.
Yeah, yeah. It's cool stuff. What'd you guys get? Did you get an answer? Or no? What'd you get, Josie?
3.82
3.82 joules. Do you guys agree with her? Yeah. All right, there's another part of this problem. What's the gravitational potential energy of the frog when he's lifted to 0.85 meters above the table? Can you figure that one out? Of course I can, Miss Kay. I got this. It's kind of a repetitive activity, but I got this. I'm going to throw the other question up there as well. Part C. Once you got part B, you can figure out part C really easily. I think. I hope. Fingers crossed. The last part says, how much work is done in lifting the frog? Lifting the frog, I should clarify. Lifting the frog from 0.65 meters to 0.85 meters. Sorry, it is. I should.
Yes.
Did you get an answer for the second part? 5 joules? Cool. All right, it's time for you guys to go because the bell doesn't work on, Fridays or whatever. So we will finish this on Monday. Remember that we have a quiz on Monday and we also have some homework that needs to be done by Friday or by Monday. Sorry. Have a great weekend. Be well.
You can do the bottom problem in 2 different ways, right?
You can, which is why we do this problem.
Because I'm doing I like the math times acceleration times this.